are so honored tonight to present Dr. Munazza Alam. She's an astronomer. She's a National Geographic Young Explorer and a most recent doctor. Alam received her BS from CUNY Hunter College in New York City and successfully defended her PhD thesis last week in the Department of Astronomy at Harvard University. She's worked in various research groups in the astrophysics department at the American Museum of Natural History, using data from Hubble Space Telescope to infer the presence of different molecules in their atmospheres. So when she collects her data, Munazza has used world-class telescopes at Kitt Peak National Observatory in Tucson, Arizona, the Mauna Kea observatories in Hilo, Hawaii, those are pretty impressive, and the Las Campanas Observatory in La Serena, Chile. So Dr. Alam, we would love to hear about weather on other worlds and studying the atmospheres of exoplanets. So please share with us.
All right, well, thank you so much for the introduction, Rebecca, and thank you so much to all of you tuning in here tonight. I'm so excited to talk to you today about the work that I do studying the atmospheres of exoplanets, or planets outside of the solar system, using data from the Hubble Space Telescope and large ground-based telescopes. And I like to think of this work as really figuring out the forecast on these distant worlds. I want to know whether these planets have clouds or hazes on them and what their atmospheres are like. And so today, in order to talk about how we do this work, how we figure out the forecast, I'm first going to start and answer this question: how do we study exoplanets and their atmospheres? I'll then jump into what we've learned so far using the techniques that I'll describe about the atmospheric properties of exoplanets. And I'll wrap up by talking about some of the future facilities that I'm really excited about that will help us to further characterize the atmospheres of these worlds. So, how do we study exoplanets and their atmospheres? To start off, I'd actually like to orient us by talking about the first exoplanet discovered orbiting a sun-like star other than our sun, and that is 51 Pegasi b, or 51 Peg b for short. So this is an artist's rendition of 51 Pegasi b, which was discovered about 2 decades ago in the mid-1990s. And this discovery changed, or rather challenged, our understanding of planetary systems and how they form. Because previously, our understanding of planets was based on the only planetary system we knew of, which is the solar system. And 51 Peg was unusual because it's a gas giant planet, so it's similar in composition to our solar system's Jupiter, but it's really close into its host star, such that a year on this planet is about 4 days long. And so because it's so close to its host star, it's also very hot in temperature, hence the name hot Jupiter. And the importance of this discovery was actually awarded the 2019 Nobel Prize in Physics. And so since this first discovery, we've made enormous progress in the discovery of exoplanets. And today, we not only know that there are thousands of planets out there, but we also know for the first time with statistical certainty that there are more planets in the Milky Way galaxy than there are stars. And so I've got a figure here showing detected planets as a function of distance from their host star, with planet mass on the y-axis, and the points are color-coded by planetary size. And what we see here is that we have a diversity of planetary systems. We see planets in tight orbits interior to the solar system orbits. We see this class of planets that are giant and close into their host stars. This is the hot Jupiters that I mentioned earlier. And we also see a class of planets that are intermediate in size between Earth and Neptune, and we call them super-Earths. And in particular, super-Earths and hot Jupiters are interesting because we see so many of them out there in the exoplanet population, but we don't have anything like them in our own solar system. And so with the 4,000 or so confirmed planets that we now know of today, the next chapter in exoplanet exploration focus on understanding the atmospheres of Jupiter's to super-Earths. And understanding exoplanet atmospheres is important for a few key reasons. So first off, ciphered in the atmospheres of these planets is information about how they formed and evolved. In particular, we can learn about how planets form by studying the composition or the makeup of giant planet atmospheres. And that's because giant planets have what we call primordial atmospheres. They acquired their atmospheres as they formed. And so by studying the composition of giant planet atmospheres, we can learn about the conditions as the planet was forming. We can also learn about how a planet evolved over time by studying the atmospheres of smaller planets. And so smaller planets are thought to be too small to retain or to hold on to their original atmospheres, but they're thought to instead have secondary atmospheres that they acquired later on in their lifetimes through a variety of mechanisms. For example, outgassing of material through volcanism or ices or other materials delivered by comets, for example.
Dr. Alam,
Yes.
I'm sorry, excuse me. I just need to ask, is there any chance we're having a little challenge on our end with the audio?
No.
Do you have a microphone that you might be able to change position of, or?
I can take my headphones out. Maybe.
Okay, want to try that?
Yeah.
Talk back at me so I can see if that helped.
Okay, is this better?
Oh, that is better.
Okay, perfect. I'm sorry about that.
Oh, that's wonderful. Thank you so much. Apologize again.
Okay, no problem. Okay, and then exoplanet atmospheres are also interesting to consider because the atmosphere of a planet controls its current day climate. So for example, the Earth's atmosphere has an ozone layer that protects us from UV radiation from the sun, and we've known for centuries that there's storms on Jupiter, such as Jupiter's Great Red Spot. So by studying the atmospheres of exoplanets, we can not only better understand the diversity of planetary compositions, but we can also better understand our own place in the galaxy, our own solar system within a cosmic perspective. So how do we study exoplanet atmospheres? Well, one technique that we use relies on observing planets when they transit or pass in front of their host stars. And so here, the yellow circle is the host star. The planet is shown by this black disk, and then the surrounding ring is the atmosphere of the planet. And so when the planet passes in front of the star during transit, it will block out a small portion of the starlight that is comparable to the size of the planet. And so what we'll observe is a dip in the brightness or the flux of the star, which is shown here on the bottom. And the size of this dip is proportional to the size of the planet. And this is because, and so we can use this technique to discover exoplanets, but we can also further use this technique to characterize their atmospheres. And the reason why we can do this is because if a planet has an atmosphere, then the size of the dips in the starlight will actually vary with wavelength. So this technique for characterizing exoplanet atmospheres is called transmission spectroscopy. And I've got a cartoon here illustrating this effect for a planet in transit. So on the left, again, I got the planet core shown in the black circle, the planet atmosphere shown by the surrounding ring, and then I show the star observed at different colors or wavelengths of light in the background. And so what we see is that depending on what wavelength of light we're looking at, the atmosphere can appear more or less opaque. And the planet will actually appear larger at wavelengths where the atmosphere is more opaque. And those are wavelengths where absorption by atoms and molecules that are present in the planet's atmosphere will occur. So we can actually go backwards and figure out what the planet's atmosphere is made of by observing the size of the planet at different wavelengths. And that's a measurement, which I'm showing here on the right in a cartoon. And this measurement of the size of the planet at different wavelengths is called the transmission spectrum. And so all of the little bumps and wiggles in the transmission spectrum are fingerprints of absorption by the atoms and molecules that are in the atmosphere of this planet. So, and just to kind of give a sense of size, so the amplitude of these bumps and wiggles, the size of these spectral features that we're seeing in the transmission spectrum, they scale by a couple of properties of the planet. For example, the temperature of the planet, the surface gravity of the planet, and the composition of the planet's atmosphere. And to just put a number in this, so for the best case scenario, so that would be a giant planet, a hot Jupiter, with a puffy kind of light extended atmosphere, would have bumps and wiggles, spectral features that are roughly 1/10%. So that's minuscule. So we're really looking for very small variations in the size of the planet at different wavelengths. And if we want to move down to smaller planets, that number shrinks even more. So we're looking for signals that are about 1/4%. So this is a difficult measurement to make, but nonetheless, we've learned a great deal about exoplanet atmospheres using this technique. And we can actually use it to not only discern the abundances or the quantities of different molecules in the atmosphere of the planet, but we can also learn about whether or not a planet has clouds or hazes on its atmosphere. So clouds in particular reveal themselves in the transmission spectrum because they affect the shape of the transmission spectrum. So if we have an exoplanet with no clouds in its atmosphere, for example, if we're looking at the fingerprint of sodium absorption, for a cloud-free planet, this sodium absorption feature would be very well defined. So we would be able to see the full feature, the peak of the absorption line, as well as this drop off in the line wings of the feature. However, if we had a cloudy exoplanet, then the clouds would actually block out a portion of the line. And so we would only actually be able to resolve the peak of the line core, for example, but not necessarily the full feature, the line wings. We can also observe different layers of an exoplanet's atmosphere by observing at different wavelengths of light. And that's because different atmospheric layers are affected by different irradiation wavelengths. So this is a diagram of the atmospheric structure of a planet that is irradiated by its host star. And we can see that in the visible and the infrared, for example, we're probing the deepest atmospheric layers. And in particular, in visible light or in optical wavelengths, we're sensitive to scattering by clouds and hazes, as well as absorption features from sodium and potassium. And in the near infrared, we're sensitive to absorption features from water, methane, carbon monoxide, and carbon dioxide. And then in the ultraviolet, we can probe upper atmospheric layers. And it's really interesting to observe at these wavelengths because we can learn about whether or not the atmosphere is escaping from the planet, for example, if there's lots of intense irradiation from the host star. So by observing at multiple wavelengths in the optical, in the infrared, and the ultraviolet, we can simultaneously probe a planet's entire atmosphere. So these are some of the techniques that we use to understand exoplanet atmospheres, which brings me to what have we learned so far using these techniques about exoplanet atmospheres. But before I get into the what, I first want to talk about the how. So one of the pioneers for exoplanet atmospheric work is the Hubble Space Telescope. So the atmospheres of giant planets are actually accessible with current instruments that are mounted on the Hubble Space Telescope. And the first ever exoplanet atmosphere was detected with Hubble back in 2002. And those observations showed evidence for sodium absorption in the atmosphere of a hot Jupiter. And so since this first detection, we've observed the atmospheres of a handful of giant planets. And we now know that there are a diverse range of hot Jupiter atmospheres. So I'm showing a plot here from a study a few years ago that kind of shows the best of what we know for gas giant planet atmospheres. And so there's a lot going on in this figure, so I want to step through what's happening. And so each curve here is the transmission spectrum for a single planet. The points are data that were taken with the Hubble Space Telescope in the optical and in the infrared. And the lines here are showing models, so theoretically possible atmospheric compositions that match the data. And we find what the kind of best match is by fitting thousands of possible atmospheric compositions to the data and seeing which one fits the best. And so that's plotted here for a sample of 10 hot Jupiters. And this study was actually the first example of comparative exoplanetology, this idea of comparing the atmospheric properties for large numbers of planets. And so in this wavelength range, we expect to see evidence from sodium absorption, potassium absorption, and water absorption. But looking at this figure, there are some planets that show evidence of sodium absorption, but some that don't, for example. And as I mentioned before, this difference in whether or not there are absorption features that we can observe can potentially be explained by whether or not there are clouds in the atmospheres of these planets. And so what this figure really tells us is that there's a range of planetary atmospheres that range from cloudy to clear. We've also learned a lot about the atmospheres of smaller planets, and in particular that the smaller planet atmospheres have properties that are different from those of hot Jupiters. And so here's a figure that's similar to the one that I showed on the previous slide, where again, each curve corresponds to the transmission spectrum of a single planet, and the points are observations taken with the Hubble Space Telescope, but this time only at near-infrared wavelengths. And these are observations for 6 super-Earths, which I mentioned earlier are planets that are intermediate in size between Earth and Neptune. And so the points are observations taken with the Hubble Space Telescope, and the lines are the models that best match the data. And in this wavelength range, we would expect to see a fingerprint of water absorption. But what we immediately notice here is that the transmission spectra for this sample of smaller planets don't really show any significant bumps that indicate absorption from water. And in fact, these transmission spectra are largely flat. In fact, this last line down here looks extremely flat, and I've actually heard some folks kind of in passing say that this is astronomy's flattest line, jokingly. And so the trend that we see here, this kind of lack of absorption features, could either be due to really thick clouds in the atmospheres of these planets, or perhaps it is that these planets have thin atmospheres that we aren't able to detect with our observations. And so this is something that is still an open question, and we're looking to explore. I also wanted to highlight an exciting result from a paper that I recently published analyzing Hubble observations of the atmosphere of a hot Jupiter. And so this figure has a lot going on in it, but I just want to kind of point out something that's relevant to what I was talking about earlier, which is that so the points here are the observations from the Hubble Space Telescope, and the shaded colored regions show models that we fit to the data to see what possible atmospheric compositions best match our observations. But the remarkable thing that we note is that we actually see the full feature of the sodium absorption line over here. So we see the line core of the sodium feature as well as the wings of the sodium absorption feature. And this is really exciting because I mentioned before that when I showed a cartoon that we would expect to see this for a cloud-free planet, but most of our observations to date show evidence of clouds in exoplanet atmospheres. And I was really excited to find this because this is the second time that we've actually ever observed the full absorption feature with the line wings for an exoplanet. And it's actually the first time that we've ever observed it for a hot Jupiter and the first time that we've ever observed it from space. And so I was really excited about this finding, and this result was also featured in the news. And then there are some interesting headlines associated with this, focusing on the clear skies for this planet, touching on how this is the first cloudless Jupiter-like planet, talking about its clear atmosphere, and discussing kind of the smoking gun evidence, this the observations which show the line wings of the sodium feature, which point to this planet being cloudless. And so this is a really exciting project that I worked on, and I thought that it would be interesting to share. So now that I've highlighted some work that was done with the Hubble Space Telescope, I also just wanted to note that we've also made a lot of progress in exploring exoplanet atmospheres using large ground-based telescopes. So I'm showing here the Magellan Telescope, which is located in northern Chile at Las Campanas Observatory. And this telescope is an example of one of the many ground-based facilities that have been used to observe planet transits and do transmission spectroscopy. And although we've made great inroads thus far, I'm also really excited about some future facilities that are going to be available soon that will help us to further characterize exoplanet atmospheres. And I'll talk about one space-based facility and one ground-based facility. So first off, these new facilities that I'm going to talk about are going to be coming online and available within the next decade, and they will truly revolutionize our understanding of exoplanetary systems. So one new telescope that's coming online soon is the Giant Magellan Telescope, or GMT for short. And I've got a mock-up here of what this telescope will look like. So to start off, GMT is part of a class of extremely large telescopes that are going to be the next generation of telescopes. And so just kind of for scale compared to the GMT, I'm also showing a truck here to see how kind of minuscule it looks compared to the telescope. So the Giant Magellan Telescope is currently being built at Las Campanas Observatory in Chile, which is actually an ideal location for a telescope. So we really want to build telescopes in locations that are remote and far away from light pollution, so we can have dark skies. We also want to have our telescopes in dry locations like deserts, since humidity isn't good for telescopes, and kind of if it will rain frequently, that's not good for observations. And we also want our telescopes to be located at high altitudes, because those are the altitudes at which Earth's atmosphere is thinner. So we have less atmosphere to look through as we were making our observations. And GMT is actually being built at one of the highest and driest locations on Earth. And when the GMT is finished, it will actually be the largest optical telescope ever built. So it's we really get a nice clear picture of exoplanet atmospheres by observing with this telescope. The other telescope that I'm really excited about is the James Webb Space Telescope, which will be the successor to the Hubble Space Telescope. And it's actually scheduled to launch in October of this year. And so James Webb will be in space. And so we won't have to worry about the Earth's atmosphere or weather or humidity. And what's really exciting is that we learned so much with Hubble. I shared some of the results that we found, and kind of the main takeaways that we've learned about exoplanet atmospheres using Hubble observations. And James Webb is going to give us an even clearer picture. Webb is going to be an improvement compared to Hubble in terms of the spectral resolution, kind of how sharply we can see all of the bumps and wiggles in the atmospheres of these planets. It's also going to give us data that is about 10 times more precise than Hubble. So the error bars, the uncertainties on each of our measurements will be much smaller. The spacecraft itself will be much more stable than Hubble, which is already fairly stable. And we'll also be able to observe at a wider wavelength range and be able to observe different atoms and molecules and the fingerprints that they have in the atmospheres of these planets. And when I think about these numerous planets that we'll be able to study even more with these upcoming facilities, I really think of it as a
Hi, folks. Looks like we have a bit of a challenge here, and that we've lost Dr. Alam's from lost her connection completely. So sent her a message letting her know that we do not see her on screen. She appears to have completely dropped off. Stay tuned. We'll work on this. Aha, it appears that you're back.
Yes, I'm so sorry. My internet cut out. I had to join a hotspot. I'm so sorry.
Oh my. Wait till can you fix that too for us? I mean, now that you're going to find these exoplanets and figure out their atmosphere, can you just figure out our hotspots and Wi-Fi connection challenges, Dr. Alam?
I'm so sorry. The weather up here is actually kind of bad, so I really apologize.
Gotcha. Oh, no problem. Thank you. We're so glad you're back.
Okay, no problem. Well, I would love to answer some questions and to chat with some of the folks here today.
Oh, well, that's fantastic. We do have a question or two here, and hope that I'm going to be able to do this justice. I think this came in when you were on around the slide showing sodium chloride in the wings you were describing. Stephen wants to know or mentions there's a lot of data, but also a lot of model points. So he asks, are the fits under constrained or over constrained?
Yes, that's a great question. And I will just reshare my screen so I can show the figure as I am talking about it. Okay, so Stephen was asking about the fits to these models. So all of the points are our observations, and then all of the lines are the models. And so the models have much higher resolution. They have many more data points compared to our observations. And if you, I mean, as you've astutely pointed out, it seems that some of, like, for most of these observations, it seems that the models are kind of under constraining, or they just don't look like such good matches. And so the way that we actually do these fits to match the observations to our data is we bin the models down to the same number of data points as our observations and then do the fits. And because we're comparing grids of models, we're fitting thousands of models to the observations. And so we're looking for the best fit among those models. And sometimes the best fit doesn't even look so good by eye. But we do make sure that it's the best fitting or the best matching model compared to the set of models that we are fitting.
Okay, fantastic. Also, we've got Sean asking about the scope launch. Are you worried that there's going to be a further setback in the James Webb telescope launch? She smiles and laughs.
Thank you so much for this question. So I mentioned that the James Webb Space Telescope is scheduled to launch in October of this year, but its original date, I think, was maybe October of 2018, so a couple of years ago. And so logistically, it's kind of just been getting pushed back for a number of reasons, just kind of timelines of getting things together. The spacecraft itself is actually kind of complicated in the way that it's built. It has a shade that's set to open after it is launched. And so kind of all the logistics, these literally moving parts, need to really be carefully thought about, and kind of the logistics for planning that out needs to be finalized and kind of perfect. And so they won't launch the telescope into space. It's very expensive. It's cost billions of dollars unless we're absolutely certain that everything will be a go. And so while I'm keeping my fingers crossed that the launch date, which is actually Halloween of 2021, doesn't have anything spooky happen with it, and that it doesn't get pushed back even farther. The exciting thing is actually just 2 weeks ago at this point, the selections for the first cycle or the first set of James Webb observations was announced. And so the programs and the observations that we're going to do with this telescope are already selected. And so it's really just a matter of keeping our fingers tightly crossed so that we can get these observations.
So it sounds much more advanced than Hubble.
Yes.
Yeah. More moving parts, more delicate.
Yes,
pieces.
it's much bigger than Hubble.
Okay.
It has a moving part, which is it has a star shade that's going to open after it is launched in its location, and it's also going to be at a location much farther from Earth. So Hubble is in orbit around the Earth, and so historically, when there have been problems with Hubble and that need to be fixed, we have been able to send people up to the spacecraft to fix it. But with James Webb, it's going to be farther out from Earth, so it won't be in orbit around Earth, and so we won't be able to send anyone out there to fix things. So we really
once it goes, right?
Exactly. So we need to be extra certain before we send it out.
Okay, very good. Any other questions? Please go ahead and use the question box. Okay, how long do you think this guy will be in service once the James Webb gets launched? Do you have an estimate?
Yeah, so I think the nominal mission lifetime and kind of like the plans that were submitted to Congress were fairly short. I would say 5 to 10 years, but I expect actually the telescope to be in operation much longer. So Hubble, I think, was also very similar. Kind of the plans that were sent to Congress were for a nominal, like a short kind of time period for the mission. But Hubble was launched in 1990, and so it's a little over 30 years old and has been going strong. And so I'm gonna knock on wood for that, because it's kind of the gift that keeps on giving. And so yeah, so I mean we build these things strong. And so
conservative estimate is always better, right? And then a better, more longevity is just an even better outcome for all of us.
Exactly, and that's also the case with some of the spacecrafts that have been sent to solar system bodies too. They have lasted much longer than we thought that they would.
And I'm sure this is a naive question, but you were discussing the cloudy versus clear atmospheres, and the fact that the discovery of a cloudless. What does that mean to you, or what is the great differential, if there is one?
Yeah, so what's really exciting to me about cloudless planets, so clouds we expect them to be ubiquitous. We expect them to be present in exoplanet atmospheres kind of widely, because at least if we look at the solar system, the bodies that have substantial atmospheres have clouds in them. And so we would expect the same for exoplanets. But in the case that we don't see clouds in our observations, that helps us have a kind of unhindered look into their atmospheric compositions, because I mentioned that clouds kind of block parts of the fingerprints of absorption, and so it's hard to kind of tell exactly how much the quantities or the abundances of these species are. And so in the absence of clouds, we can really precisely measure exactly what the compositions of these atmospheres are.
That makes sense. Okay, so Dr. Alam, I did get to learn a little bit about you in the preface to this meeting, and you shared that one of your passions were really how you grew up and chose this profession, if you will, is because you're so passionate about sharing science with us and outreach to the public. And I believe I can understand why you are so good at that. You've obviously got a passion, and you can make tremendously detailed and complicated science come to life here, and I can see your enthusiasm. John would like to know if you might have any insights on the potential organic molecules found on Venus.
Ooh, Yeah, so this is something that was in the news a few months ago or last fall. So there was a paper that was publishing the detection of phosphine on Venus, which may be a potential biosignature or a molecule that may hint at potentially at the existence of life. And so there's been a couple of kind of back and forths between some teams that have analyzed these observations. So the first team analyzed observations and found evidence of phosphine, and then some other teams later on then reanalyzed those data and didn't find that evidence. And so it seems to be an open kind of question at the moment, but I think the reanalyses that don't show evidence for phosphine are convincing. And so it doesn't mean that, you know, that this particular molecule isn't the way to go, or kind of the focus of other kind of biosignature searches in planets, but at least for Venus, it seems like we need to keep looking.
Okay, and for those of us who are not in the technical science fields, what is phosphine and why are we concerned?
Yeah, so phosphine is a molecule that has phosphorus, the element, and hydrogen kind of bonded together. And there's been some work kind of looking at the chemistry of the atmospheres of these planets, which are hot and they have very kind of extreme temperatures and pressures. And so it's thought that if we see this molecule in the atmosphere of a planet, it might be a byproduct of some biotic process. And there's some other kinds of molecules that we think of that kind of fall into this category of biosignatures or fingerprints of life. The ones that we think of more commonly will sound more familiar because we have them in Earth's atmosphere, like ozone, for example, and O2, oxygen. So phosphine is a little bit more exotic, but we kind of need to think a little bit more exotically when we consider these exotic worlds with higher temperatures and conditions.
Right. Okay, very good. Fascinating. Hold on, here's another one. Sean, okay, loaded question. Sean, you've got them all tonight. Here we go. What recommendations could you make to help expand the diversity in the STEM field and make it more inviting to women? There you go.
I love this question. So I think about this a lot, and I think that there are a lot of different things that we could do, a lot of different avenues that we can take to kind of make sure that STEM fields are more inclusive of women, of people of color, for people from all different walks of life. But one of the things that I think is the most important is not even to start with diversity, but actually to think about other related topics like inclusion and equity. I've started to think about it this way because I like to think of it as an analogy with a party. So there's the idea that you can invite lots of different people to a party, but you don't have to talk to them. And so that's kind of what, so you can invite a whole bunch of people to join STEM fields and increase the diversity. But if we increase the diversity of these fields, but we don't include or support these people, then we're not being inclusive. We're not talking to them at the party. And so one of the things that I think is really important is making sure that we're being inclusive at every step of the way. And we're kind of in a transition period in which we need to we are not yet seeing the diversity that we're working to inculcate kind of at more early career, more junior levels, at senior positions. And so we'll have to take some time to wait for these people to be supported and take on those positions. But in the meantime, while we're at that, we should definitely make sure that we are including and supporting and mentoring and caring for the diverse groups of people that we are inviting to STEM fields.
And with that, and with my own age, should I say. The times currently are so much different in the opportunities and inclusion of women in science. It's quite amazing to be witness to that, and to see the progression. Very good. Let's see, I think I see something here. Open question. Were you always interested in astronomy? So I know you told me some of your family history. Tell the audience a little bit what your family does, Dr. Alam.
Yeah, sure. So I do come from a family of scientists or science oriented folks. So my dad has a background in physics, my mom has a background in biology and chemistry, and I have two older sisters. One of my sisters is a chemist, and my other sister is a biomedical engineering by training, but she's currently a high school math and science teacher. And as for me, I actually didn't have a childhood interest in astronomy. I didn't have a backyard telescope. I didn't watch space movies. And I think a lot of that is largely because I grew up in New York City. So a backyard telescope really wouldn't have helped much in general, but I was always really curious about the world around me, and my family always encouraged me to ask why and think about the ways in which the world works. And so one of the subjects that I learned that I really loved is physics in high school. And because it was a way to really understand the world around me and to better contextualize it. And so I knew when I started college that I wanted to study physics. And I remember that I met with a scheduling advisor, and I thought that I was so ahead of the game because I came in knowing what I wanted to major in. And my scheduling advisor was like, well, that sounds great, but what are you going to do with this? And she kind of presented some options to me about potential professors that I could reach out to see kind of career paths with physics. And I ended up connecting with a professor who was running an astrophysics research group at the American Museum of Natural History in New York. And I didn't have any experience, but I was interested and willing to learn, and that's kind of how it all got started.
I don't think I could have had a better softball. Connect your children, your girls, your family, and your neighbors with your local museum. I love it. That's fantastic. And talk about a science powerhouse. What a family. Holy cow. So don't underestimate, right, the impact of those around you in your formative years and what they are prescribing as important to be in your life at that time, because we're all a product of that. That's just fantastic. Absolutely. Okay, well, I thank you. I see that we're running up to 7:16. So what a wonderful talk. And again, congratulations for your last week's defense of your thesis. How exciting for you. And we're thrilled that you were able to join us here. And please, come to Southeast Virginia. It's a beautiful locale, and we absolutely welcome you. Come into the museum and explore what we've got going here. Please, we'd love to have you. And if you're going to be with us next month for Naturally Speaking, brought to you by Virginia Health Services, we're going back on land here, folks. Next time, May 20th, we'll welcome Dr. Matthew Lamanna. He is the Mary R. Dawson Associate Curator, Section of Vertebrate Paleontology. Back to the vertebrates, Carnegie Museum of Natural History. He is also a National Geographic explorer, and he'll be talking to us about bigger, stranger, and maybe scarier even than T-Rex, meat-eating dinosaurs from the southern continents. And he's going to feature some of the dinosaurs that will be coming here for our seasonal dinosaur exhibit called Jurassic Giants, and that opens May 29. But join us on May 20th.